I guess the question is, are they gonna be more bustling than they were in the fall?
Hard to know.
Yeah.
Fall is pretty bustling too. At least I'm not teaching compilers. Next fall, when I'm teaching both algorithms and compilers at the same time.
Oh, hey, why do that to yourself?
I chose that.
Okay.
Yeah. Yeah.
Oh boy.
The two highest demand office hours classes at the same time. What is a life? What are all of my other obligations? All right, we were talking about the Bellman equation last time, so we can dive into this. Again, I want to start basically from the beginning of this, because I think it's important to understand this recursive relationship between a state and the next state, or the set of possible successor states. So maybe instead of using tic-tac-toe, I'm going to use something else that we've heard and seen before. Anyone have a particular turn-based game they would like me to use as an example? I could default in chess, but literally anything else that is turn-based that everyone's going to know, or close to everyone's going to know.
Let's just shoot for D&D since that's another popular one.
Too many states, too many successor states.
Connect four.
Connect four.
Four. Ooh, that's
Yeah, that would work.
Oh, the advanced TikTok.
Yeah, so
Yes.
and there's a bit of a hidden value within Connect 4 as well. How would you come up with a reward function for Connect 4? That's a good starting question. What does a value of a state mean? If there's Connect 4 and you have black on one peg, red red on the next, and red on the next, what is that? What is the value of that to black, or the value of that to red? How would you come up with a reward function? Don't use that as an example necessarily, but I'm just giving you, that's a state, and it is red's turn, but it should still be probability of winning or change in probability of winning. But how would you define some kind of heuristic for probability of winning in a game like Connect 4? It's a little bit more complicated, I think, than other games, but you could start with something like, how many pieces do you have in a row? The maximum number of pieces you have in a row where there is an opening on one side or the other for another piece to be added to it. You could look at how many columns, if the opponent plays in, then you can play in and win. So are you removing or reducing your opponent's search space for how many moves they can make? Because as soon as they move in a particular location, they lose the game. That constrains them in some capacity and makes it so that you can manipulate them more with your other moves. You try to force them to have to play there. So that's what that would look like. If we're going to take the Bellman equation and put this into a Connect 4 term, a state is just a snapshot of the board plus whose turn it is. Your action space would be all of the columns, because as soon as you place your piece in that column and it falls down to where it goes, that is your move. You choose a column. You don't choose a level within that column. You just choose which column you are playing in. So that would be your action space. A policy would be a way of determining with what probability are you playing in each one of those columns. What would the associated variables be that would change, or have you changed your strategy for which column you play in? You might start with a random policy. If you'd never played Connect 4 before, you didn't even know the rules necessarily. You just knew, I place a piece in one of these columns. Okay, I can do that. But you don't know what wins the game, what loses the game, what causes winning the game or losing the game. You'd have to learn that from scratch. How do you go do that? Well, we take the idea of a state, we take the ideas of actions, and eventually those actions lead to winning the game or losing the game. And you can start to back propagate that information from that winning state or losing state to the state where you made a decision right before you won or lost. And with enough information, you can start to back propagate that all the way through the state space of the game. Then you could start coming up with some meta variables of when I make this kind of move that gets me 4 in a row, I win the game. When I make a move that allows the opponent to get 4 in a row, I lose the game. That would become apparent with enough information, enough data, that is the win condition. You wouldn't even need to know that at the beginning. There would be a correlation of this component with winning and losing and the associated rewards. So you would learn to prioritize that which gets you 4 in a row or sets up a position where you can get 4 in a row, or avoid setting up positions where the opponent can get 4 in a row. But we care about not necessarily visualizing the entire space. You can imagine that we're in the middle of this situation where we've learned some information. We have approximate values for each of these states. If we wanted to figure out the value of a state, we could say if we know the values of all of the possible successor states, how good is it that I placed my red piece in each one of the possible columns? Some of those would lead to better outcomes or better positioning, and some of those would lead to worse outcomes or worse positioning. These are all of the S primes, the possible states after you make your action, and probably also after the opponent has moved. So both you have the decision of where am I going to place my piece, and then probabilistically from there, where is the opponent going to place their piece? Just because I place my piece in the first column, the opponent could place their piece in the first column, second column, third column, fourth column, etc. So that's going to be the branching factor from this action down to all of these S primes at the next level. So this is a recursive relationship between a move and all possible places that the game could be, all states the game could be in when it is your next turn. Does that make sense? So to calculate how good is it to be in this state, we're going to look at for every possible action that we could take, for every possible state that could come when the opponent moves after my action. Each of those have their own separate values. If we knew what those values were, we could figure out the probability of given. So I guess first we say we have a policy. The policy tells us with what probability we're going to select the action, with what probability we're going to select putting it in the first column, second column, third column, fourth column, etc. Given that we're in this state, we would have a completely separate distribution for every possible state that the game could be in. That's a lot of possible states. But the probability of moving in the first column is going to differ between whether that wins me the game or whether that sets up the opponent to lose the game, or every other possible situation between those extremes. So for every possible action, and the action space is determined by the policy, we're just going to use a random number generator, and we're going to figure out which move to take, weighting each one of these moves based on how good the policy thinks it is to make that move. We're just following the policy. The policy might say if we get a number between 0 and 0.4, move here. 0.4 and 0.7, move here. 0.7 and 1, move here. That would be a 40%, 30%, 30% distribution over which of these 3 possible actions to take. Given that we make that decision, now there is an additional branch of everywhere that the opponent could move. Once the opponent moves, then it's your turn again. You don't make any decision between when you make an action selection and when you find yourself in one of the possible next states. That's based on the opponent's move that you can't control. When you do find yourself in that state, you would be able to figure out, if you could understand based on your past history, when I've been here and made this action, my opponent chose this 80% of the time and this 20% of the time. You could say, since I'm choosing this 30% of the time, and the opponent chooses this 80% of the time, the value of this action is now 80% of the value of this, plus 20% of the value of this. You can back propagate that to figure out the value of taking this action in this state. So if we look at exactly what this value, this policy is telling us, the value of a policy in a state, this is telling us how good is it to have a particular action selection function at a particular state. How good is it to select this 40% of the time, this 30% of the time, and this 30% of the time? Do we agree that the value of this state is different if we follow a different policy? If we just choose this 100% of the time, that changes the value of this state. Because we no longer care about these states, we can never get to them. The amount of time that we spend or how frequently we end up in each of these successor states is dependent on the two variables of the policy, how frequently we choose these actions, and how likely the opponent is, given that we pick the action, to pick their move such that we end up in these states. Yeah,
So there needs to be a different policy for every state that you're in.
potentially. Yeah, and you would learn from, if you're one step away from winning, the policy should, if it's an optimal policy, bias you toward the action that wins the game. And that's different from the action at the very beginning of the game, because you're not ready to win the game yet. In fact, you have next to no information about that. The game hasn't unfolded yet. So the policy will tell you, given the state, what distribution of actions to take. And we can learn from experience. We'll get into what it's like to change your policy from experience. We're going to basically say, with the information that we've gathered, the policy that we're applying looks suboptimal now. So we're going to change our policy, given the information, the data that we have. We're going to optimize the return from the data that we gather. When we make that change, we're going to gather more data. As we gather more data, then it's going to look worse because of just we've gathered more data. So we'll update the policy based on the data that we gather, with the goal of optimizing this action selection to maximize the total return or the total reward received. So it's just an optimization function. But breaking it down into the math, we see the value of a policy in a particular state is just the sum over every possible action. This just says the value basically of how likely are we to take each one of these particular actions. According to the policy, how likely is it that we take an action given that we're in that state? So this breaks down into, in this picture, for summing three things. If this is move 1, move 2, and move 3, we would have for move 1, what is the probability? How likely are we to take move 1 given that we're in this state? According to my last example, that was 40%. We would just say this becomes 0.4. And then we look at every possible move the opponent could make for all possible states that we could end up in after the opponent makes their move, and reward for that. How much does that improve your chances of winning? What is the probability? So this is your guess at your opponent's, how likely your opponent is to make the move from there, to end up in S prime and receive the reward that you get from that, given that you started in the starting state and chose this action. So that probability, the actual value of being there, is the reward that you receive from that, your increase in chance of winning, plus some discount rate times the value of being in that state. The reason we have a difference between the reward and the value is sometimes we have a step parameter. The reward would be something like you get a -1 for every turn. Or this is back to our maze example of we want to prioritize solving the maze faster rather than slower. So the reward is just usually a time step or something that biases you in one way, shape, or form. And then the value would be your estimate of probability of winning from that point. How good is it to be in that state that you end up in? So we're going to now come up with the value for this state based on every state that could follow that state, multiplied by the probability of getting there. The reason why we multiply these two terms is they're just successive. We choose the action, then the opponent chooses their action, and then it's our turn again. How good is it to be in this state? To answer that question, it depends on every state that could follow, and how likely every one of those successive states is we already get there. If there's an action that we could take that loses the game, or basically loses the game for sure, then we will find that we don't take it very frequently, or it contributes a large and negative value to this overall function if we are prioritizing it too much. feeling a little bit better about Bellman? Do we see that concept of a recursive relationship between the value of a state and the value of every possible successor state? It creates a big tree. In tic-tac-toe, the value of the starting state is based on the value of every successor state from there, and the value of each of those is based on the successor of those, which is based on the successor of those, which is based on the successor of those, as deep as the game could run. This becomes very complicated very quickly. It is exponentially complicated with respect to the size of the problem. We'll talk about when this is useful and what we can do when we can't measure it. Yeah. Any questions on this before we move on to talking about optimal policies? All right, let's talk about optimal policies. So a policy can't just start out as a random policy. We just randomly select the actions that we're going to take. But an optimal policy is one that maximizes the value of a particular state. So a policy has been optimized with respect to a state. If given the information we have, we could not change the weighting of the actions in a way that improves the value of that state. As soon as I make any tweak, any change at all to any value for any one of those actions, the value of being in that state decreases. So we call V star of this. It is the best possible policy for that particular state. And the best policy, what we mean by that is the best action selection. How likely are we to pick each of these different actions? If we made any change, it would decrease the value of being in that state. We can do the same thing for action values, because remember that sometimes we don't want to look at the value of being in a state. We want to look at the value of being in a state having already selected the next action. That puts the first variable on how does my opponent respond to that move. And so it's the best possible policy for that given the action selection. So this takes the state as a parameter, this takes the state and the action as a parameter. And the best possible policy that we can have is the best action selection such that we maximize the value of being in a state or maximize the value of being in a state and selecting an action. So plugging this idea into Bellman, instead of now looking over all of the actions, we want to pick the best action. So how do we optimize when we have different decisions in a state? It's really easy. We just pick the best action and always do that. If we're trying to optimize and we can win the game or potentially win the game or lose the game, what's the action we should take? The action that wins the game. So if we're trying to optimize a policy, if we're looking at the state value function, instead of assigning a probability to these different actions, we're just going to take the maximum. Whichever one puts us in a position where the distribution that we're aware of here maximizes the value of that action, we just take that action. There's no reason to probabilistically look at different actions unless we're trying to gather information about what looks like a suboptimal move. We're trying to explore, then there's reason not to do that necessarily. But if we're looking solely to optimize and exploit the information that we are aware of and know, then we should take the best possible action all the time. And it takes away one of the sums from the prior problem. We just look at the probability that your opponent puts you in state S prime with their action, and the reward that we get discounted by taking an extra step, that we took an extra move. And that gives us the optimal policy for that state. If we're looking at state action pairs, it's a little bit more complicated, but just recognize the first thing, we've already selected the action. So the first thing we have to do is sum over every possible move your opponent could take. Once the opponent takes the move, then we must select the next action from that next state. And that puts us back in the same position to have looped to that, going from one state action pair to the next state action pair. You can't stop at the state because we haven't selected the action yet. If we're gonna loop this process, we have to go from, there was a state above this, we selected this action. There are now multiple states we could end up in based on an opponent's selection of an action. But then we take the maximum of the actions from there, and that puts us back in the state action pair where we've been at a state and selected an action. So that's how we would analyze state action pairs. So this is a way to relate Bellman optimality. How would you solve this system? So now we have a number of states to do this with. How would we figure this out? We could get experience, but if we know the underlying system, we know the opponent's action selection algorithm, this becomes a linear system. We have the number of possible states in our game equations and the number of the number of states in our problem unknowns. So we can solve a linear system, a massive linear system, and the result of that is that we end up with a perfect optimal policy. But the big assumption that we are making when we do this, we're making three big assumptions. We need to know all of the dynamics of the environment. That means we need to know our opponent's action selection algorithm. We need to know any underlying probabilities of how likely we are to end up in successor states, given the states that we make, the states that we're in and the actions that we take. That's a big stretch for a lot of environments. We also need extreme computational power because, as you've seen with solving linear systems in a class like linear algebra, that takes a while as we scale the number of terms and unknowns. Imagine having thousands or millions of them. How long does that take to solve? We also need the Markov property to hold, which means that it doesn't matter how we ended up in this state. All that matters is that we are in this state. To give you a sense of what that means, because of the simpler, I'll go back to tic-tac-toe. Two progressions. X plays here. Then O plays here. Then X plays here. Game two. X plays here. Then O plays here. Then X plays here. With regards to what we should do from either of these states, does it matter how we got there? The sequencing of plays when X played first, then O played, then X played. Does the prior sequence matter in determining where O should play next?
No.
Not at all. That's the concept of the Markov property. All that matters is the state that we are in, not how we got to that state. We don't have to store the history of moves because it's not going to affect our action selection at this stage. You can imagine in a larger branching game like chess, on the 30th move, you end up in exactly the same position and you took a vastly different path of getting there. What you should do from there has nothing to do with that history, so it's not worth storing because it doesn't affect how you decide your next move, your next play. Any questions on that? So, yeah,
Counter example.
where the Markov property isn't needed, like the history does matter.
Yeah.
It could be something like, let's see, where does history, the exact instance, matter? You could be at the same financial situation, but the way that you got to that financial situation burns some bridges or doesn't burn some bridges. So the actual actions that you could select from, maybe as a way of gaining wealth, you have destroyed two friendships versus not destroyed two friendships.
In different states, though, I think so.
Well, we saw that if the state is the financial situation, you have the same amount of money, but the actions that you can take are a bit different from from that because either you have some opportunities or you don't have some opportunities. Then this whole system wouldn't apply because the states look different because the way you got there affects the current state. In this case, the way you got there does not affect the current state. You could argue that those are different states depending on how much information you're storing in the state variable. That was a strange example. Yeah, I can come up with some more. A little bit of time to think about it. So yeah, approximation is usually our best route to this because of these reasons. There's a ton of computational power, and we are not going to be able to solve the entire system in one swoop, if we even understand the underlying components of the system. So we should do something or have some process that allows us to iteratively converge on the answer rather than try to solve the answer outright. And if we can iteratively converge on the answer, then we can stop that iterative process once we are close enough to see that convergence happening. And that can take a lot less time and is a lot more scalable than trying to solve an entire system when the system may scale in size itself. So how do we approximate? What do we relax if we're approximating? We don't need complete knowledge of the environment. Right? If we're approximating, we can simulate. And if we're simulating, we're going to be gathering data rather than looking at the entirety of the underlying environment. It's less memory intensive, less CPU intensive. You don't need to do as much work to be able to have an approximate answer. You're never going to get a perfect answer with approximation, but you can start to take the limit. You can start to see a pattern emerge, apply the pattern, and calculate what that limit would be. You can focus on learning frequently encountered states. There are some systems where frequently encountered states are more important to learn than an average state. Take chess, for example. There are common end games in chess where you have a king, a bishop, and a knight, and your opponent has a king and a knight, or a king and a rook. Those are common end games, and when you find yourself in those kinds of states, they're worth studying because many more games will converge on that end state than there are states in that middle ground. So why study a game that you are probably never going to play or see when you could study an end game that you are more likely to see? And we'll see that when we use approximation, we're going to be ending up simulating games that the proportion of the states that we see are going to be based on the proportion that we would actually see in practice. So we'll get more experience in states that we're more likely to visit. That may mean that we're less prepared for those arbitrary middle game states, since there are so many of them, but we would be more prepared for the states that we are more likely to see. And that's probably an improvement to something like a chess engine. So the way we're going to simulate this with approximation is through dynamic programming. And we'll see that this has many similarities to the concept of dynamic programming from algorithms or compilers, wherever it is that you've seen dynamic programming before. Who's never seen dynamic programming before? Couple people. Who feels like they don't have a great understanding of dynamic programming, even though you've seen it before? More people. This is what I'm trying to fix in algorithms. But concept of dynamic programming is you're breaking problems into overlapping subproblems. And from those overlapping subproblems, you're going to be able to reduce the complexity of the whole problem by caching the subproblems the first time you see them. So rather than recomputing those subproblems, you first look in a table or look up, is there already a solution to this subproblem? If there is, then you don't have to recalculate it, it's just a lookup. Only if you haven't calculated a subproblem before are you actually computing it. And that ends up saving a lot of time where there is a lot of overlap between subproblems. So dynamic programming breaks down into a couple of different types of, there are some different ways of tackling this problem. So dynamic programming still requires a perfect model of the environment. And if you don't have a perfect model of the environment, we can take what we know from dynamic programming and apply it to either Monte Carlo or temporal difference, where we don't have a perfect model of the environment. So when we have a perfect model of the environment, dynamic programming is the right tool to use. When we don't have a perfect model of the environment, we have to use either Monte Carlo or temporal difference. And we will look at all three of these and algorithms embedded within all three of these for how to solve a reinforcement learning problem based on whether we have a perfect model of the environment. So if we don't know the underlying model of the environment, we don't have any experience whatsoever, but we know what the environment, we know how the states and actions set up. You can imagine it's kind of like a tree. If you could draw the tree, but you don't know what the weights are on the connections between the edges, like tic-tac-toe. We know what the board states are. We could draw a tree, all of the possibilities, all possible game states. We have a perfect model of the environment, but we don't know how good it is to be in any of those states. How close to winning are we? We don't know. We can learn that iteratively, but we still have a perfect model of the environment. We know every possible state, every possible action, every possible next successor state, given that we made an action. There's nothing hidden in the game of tic-tac-toe. On the other hand, there are plenty of other models and environments where we would not have that perfect information. Anyone with an example of an environment where you don't have perfect information? Yeah.
Heading straight back to the stock market.
Stock market, absolutely.
I was thinking like games again. I was gonna say like a card game where you don't know like the deck or your opponents.
Yeah, if you're imagine learning a game for the first time. You don't even know what actions are available to you necessarily until you're at a particular state. You would ask the expert who you're playing with, what can I do right now? And then they could tell you, but you wouldn't necessarily know what would happen after that. You just kind of make a best decision that you can, given the knowledge you have at the time. Real life is a great example of a model that you can't use dynamic programming on. What are the next successor states if you choose to take elective 1 instead of elective 2? Who knows? You're going to make a decision and you're going to deal with the consequences. So you build the model based on experience. And imagine being able to live life over and over and over and over again, resetting whenever you died. Now, over the course of many lifetimes, you would start to get a sense of what that cause and effect are, what the action selections are at different moments in time. You'd get experience. From that experience would come the ability to make better decisions. But you don't know what the system looks like until you've lived through that system and figured out how the system works through experience. Whereas with tic-tac-toe, top down, we're looking at the system. We can fully understand the system. So that's the big difference. So dynamic programming, when we understand and know the system. Monte Carlo or temporal difference, when we don't know or understand the system and have to simulate it in order to understand it. All right, we're moving forward in dynamic programming. So we're going to have a perfect model of the environment. I'm sorry in advance. First thing to do is to go through policy evaluation. This is going to determine how good is a particular policy. You can imagine that you have a policy that says no matter what state you're in, you have some method of selecting actions in those states. It doesn't have to be intelligent. It just has to be constant. Every time you are in the initial state of a tic-tac-toe game, there is some distribution that tells you where to play and how frequently. Doesn't have to be good, it just has to exist. So we want to figure out how good it is to be in each state. What is the value of being in this state according to this policy for that policy? And to do that, we again use the Bellman equation. So this should start to look familiar. The value of being in a state is the expected value according to that policy of everything that could come after that policy, the return from there, given that we're in this state. So the value of being in a particular tic-tac-toe setting is based on everything that could follow. How many states could follow from here? What are the values of those states according to this policy? We could calculate all of that based on our current knowledge of the values of those states. So we compute that and we end up with a value. And we do that for every single state in the entire state space, which can be a lot. You don't need to know necessarily all of this math, more of the general intuitive idea of we're trying to come up with a value for each state, and that's just based on the Bellman equation. So we're looking at the value of this state based on every possible successor state, and then doing that for every state in the system. Yeah.
I'm trying to make an optimal policy, then wouldn't like most state or most actions, wouldn't you just have one that just be zero with their value?
We're actually going to see that happens quite quickly. So you can imagine that initially what we do is something that is completely random. And I'll have a couple of examples in small state space environments to see how this process works. You're going to look at the value of each state. And then, so that's just the evaluation step, because we're going to go through an improvement step next. And the improvement is going to say, given all of the actions that we have available, let's change the policy so that we improve the next evaluation. This is going to be an expectation maximization algorithm, if you've ever heard of the concept of that before, but basically you're going back and forth between evaluating a policy, improving that policy, evaluating that policy, improving that policy, evaluating that policy, improving that policy. And the reason you can't do it in one fell swoop is that the information needs time to back propagate through the values of the states. Initially, the values of the states where you've won or you've lost have real values, and everything else has an approximate value. In one iteration, we're going to be able to back propagate the winning and the losing to the states right before that, but not further than that. And then another level, we're going to be able to back propagate at a state further back and further back and further back. But as you do that, the state that's going further back, that's going to change the numbers of everything that comes after it. So it will eventually converge on those real values. Let's see how that works. I think that needs an example or a walkthrough. So that's policy evaluation. So we're going to use the iterative method for this rather than solving a linear system, because that's gross. We do an expected update. So the value at time k+1 of a state is going to be based on the evaluation, the expected value of the policy, according to the value at step k. So it is an iterative process, and we'll just repeat this for every state in a big loop. So we're going to go through the value of every state. Once you're finished with that, go back to the beginning, do it again. Once you're done with that, go back to the beginning and do it again, and continue this process until it converges. As you do that, you'll get the value of the policy. You haven't done a single improvement of that policy, but you've just gone through an iterative process of knowing the values of the states. Again, you need an example to see how that works. But here's some pseudocode for what that would look like. But I want to show you the example. So we're going to use Grid World as our example. So the goal of this really simple game is to get either here or here. And we can either move right or up or left or down. We always have the option for all four. Even if we're in a corner, we can still move up from position 3 and stay in position 3. You kind of bump up against the wall and stay there. Same thing for moving right from position 3. But the value, and of course, for every transition that we take, we get -1. So the question is, what is the value of being in each one of these states if our policy is to randomly choose each one of these actions? So you can imagine that with probability 0.25, we do each one of these actions. On average, how long will it take if we start in position 1 to reach here or here, according to that policy? That's a complicated question. 25% of the time, it's gonna be one time step. If you move left, we're done. But if you move up, we're still there. And in the following time step, if you move left, we're done. If you move down, on the other hand, there's a 25% chance of that. Now you're at least 2 moves away from reaching the goal. But you have to know what you're doing. Well, probably this whole system seems arbitrarily very complicated at this point to figure out how many moves on average would it take. But the iterative method that we just described will tell us the converging values for this are how many steps it will take from each of these squares to get to one of the check marks according to this policy. Let's take a look at how that would work. So we start off at step 0, just asserting that so far we have made 0 moves from each of these potential starting locations. These are all the states in the state space. So we've made 0 sweeps over the state space to try to figure out in one time step, what is the likelihood? What is the average value of being in that state? But you can imagine honing in on this square right here. Let's just look at what happens in one time step. So 4 options, we could move here, we could move here, we could move here, or we could move here. Regardless of which action we take, we're getting a -1 because we've taken a time step. So regardless, this is going to be, we either end up in, this was position 2, we're in position 2, and that happened 25% of the time. We're there and we get a reward of -1. And this happens for each position that we could possibly be in, but once we're here, once we're here, once we're here, and once we're here. So that's why 0.25 times -1 plus 0.25 times -1 plus 0.25 times -1 plus 0.25 times -1. At step 1, the value here is -1. Regardless, you went somewhere and the stepping there had a cost of 1. But in the instance where we went left, which happened 25% of the time, we're done. So in future iterations, that process died. So future iterations, we're not going to consider adding a negative penalty to this square because 25% of the time it ended the episode. So this is why when we look at the value of each of these other squares at time 1, they're all -1, with the exception of the 2 goals. If we started in a goal, you don't leave the goal, you're already done. So the value of the goal is 0. But the value of everywhere else is -1. When we update, imagine we made this entire sweep of this state space and came up with these values for step 1. To calculate step 2, we're going to do exactly the same thing now. From here, we have 4 possible moves that we can take. Let's come up with the expression. So if we move up, we're going to 25% of the time get value -1. So the value of being in this state is -1. 0.25 times -1. If we move right, 0.25 times -1. If we move down, 0.25 times -1. But if we move left, we've updated the value here to be -1. We've updated the value here. This stayed 0. So this is going to be 0.25 times 0. And we're going to add this sum to the -1 that we had here already. And we end up with -1.7. And for these other states, there was no 0 option. Everywhere you go is a -1. So that becomes -2. And you can start to see now that it was better to start in this state than it was to start in this state. at least from the perspective of 2 steps in the future. We're iteratively trying to converge on the value. This says that 2 steps into the game, if you start here, you're still playing, or you just reach the destination. Here, there's a chance that you stop the game early. So in 2 moves, you've only made an average of 1.7 moves if you started here. But that only tells us about time k equals 2. We need to continue to iterate and look at every possible state a bunch of times. As we get to k equals 3, we find that the values changing, this minus 1.7, will now propagate to its neighbors, not this one, these neighbors, and these values start looking better than the ones that are in the very middle. Because there's a chance now in 3 moves that you have ended the game. At time k equals 10, you can see that it's still iterating and still working. You will see that what it converges to is the k equals infinity down here. This is the actual answer to the question that I posed before. You start in this state, how many moves does it take on average to end the game? The answer is 14. If you start in one of the worst places, minus 20, why is this minus 22 worse than the minus 20?
Because the corner has less options.
Yeah, you're more likely to stay farther away. The minus 20, no matter what direction you move in, you're 2 squares away at most from a solution. But with the minus 22, if you move up or right here, you're still 3 moves away. So it turns out the corner is worse, even though the shortest path in both to a solution is 3. But that shows up here. You didn't need analysis or interpretation, you just needed to simulate the experience, and then the interpretation of this simulated experience tells you a lot about the underlying game, as simple as it is. Any questions on reading this? We'll come back to really applying the math to this tomorrow, I think. But I want to answer any questions you have about this itself and what this means and how this works. What we're doing is evaluating that random policy. Is it a good policy? No, it's a terrible policy. But we can look at how bad is that policy. We actually have numbers now rather than intuition that states how many steps it would take to end the game from each of these locations using this random policy. Given this information, it actually also tells us what we should do to change the policy. Any hints at what we should do to change the policy? I'll end class with that question. If we were trying to change the random policy based on the knowledge that we gained when we iterated this and came up with these limits. So we have this data. What does this tell us about the policy or what we should do to the policy? When we're in the minus 14, if I move right, I'm in a state with value minus 20. If I move up, I'm in a state with value minus 14. If I move down, I'm in a state with value minus 18. And if I move left, I'm in a state with value 0. Of those 4 options, which one is best?
Left.
Left. It's numerically inherent in the data. What should intuitively we do when we're in this square?
Move left.
Move left. So the data agrees with our intuition about how to now change this random policy. Instead of deciding randomly where to go from here, we should always go left. And that optimizes the pathing for this entire structure. If we look at just which direction maximizes the value of the successor state. But it took an infinite number of iterations to arrive at that convergence, or a while to arrive at that convergence. So tomorrow we'll talk about what we can do about that as well to make that process faster. So I'll see you tomorrow for that.